Okay, I think we can start. Thank you all for joining this course on learning to quantify. This course is given by myself, by Alejandro Moreo and myself. And as you know, is part of the AIDA, the AI Doctoral Academy. First of all, a couple of words of introduction. Alejandro and myself are researchers at the Institute for the Science and Technologies of Information of the National Council of Research, which is actually the largest research institutions the largest public research institution in Italy. Alejandro and myself have been active for many years on this topic, on the topic of learning to quantify. I guess that some of you might not know what it is, since it is a fairly not terribly well-known task. As a word of warning before we start, you can find here the URL for downloading the slides if in case you want them. Actually, these slides that you can download from here will cover today's lesson and possibly a first part of next lesson. So first, let's say what this course is going to be about. It's essentially a course about a special type of techniques, a special type of application context for supervised learning technology. And the context that we are going to address today are contexts in which we are not interested in predictions, in decisions at the individual level, but we're going to be interested in predictions at the aggregate level. And this has to do with the fact that there are many fields of human activity where the focus is actually on this aggregate level and is not on the micro level of individual decisions. Okay, so I've listed a number of such fields here. Some of these fields are, say, social sciences, political science, epidemiology, market research, ecological modeling, astrophysics is another, and there are several others. Okay, so in all of these fields, people tend not to be interested in individual decisions, the typical decisions that, say, classification algorithms return, but are interested in predictions that deal with an entire population rather than individuals. And the techniques we are going to discuss today actually address these kind of needs. I said that, in a sense, we care about populations. This might be populations broken down according to a number of criteria, So, for instance, in social science or in epidemiology, say in epidemiology, we might be interested in understanding the patterns of the spreading patterns of a virus, say across a certain population, and especially maybe broken down according to age groups, different geographical sub-regions, etc. So the interesting fact is that here we are not essentially interested in individuals. Okay, so epidemiologists are probably the only kind of medical people who are not interested in the individual patient, but are interested in the large picture. And this is this large picture that the quantification or learning to quantify techniques deal with. Some social scientists have said that in these fields, we don't care about the needle. What we care is the haystack, in describing and characterizing the haystack. And indeed, learning to quantify is something that you can, let's say, oppose to learning to classify, you know. So quantification is something which is as opposed to classification. So quantification stands to classification, as aggregate data stand to individual data. Of course, I mean, you might immediately think, you know, this is something that has to do with regression, and indeed it has. And we'll try to deal with the relationships between these different fields throughout this lesson. So this course is essentially an introduction to this field, to the various applications of learning to quantify, of course, I mean, to the methods for performing quantification, and to the methods for evaluating quantification systems. And the idea here is that, you know, we would like this course to put you in a condition to use and apply quantification systems to your applications if you find that your applications might benefit from this. And of course, I mean, put you in maybe in a condition to do active research, say, in quantification. On the right, you can see, you know, this is our forthcoming book. So Alejandro and myself, together with a couple of other colleagues, have recently written a book on learning to quantify that is going to be published with Springer and should really appear in the next weeks or days, you know. And it's an open access book, you know, so you can you don't need to go to pirate sites in order to get it for free. You can download it for free from the URL indicated in the footer. And at this URL, you know, you will, well, for the moment being, we have the proofs, you know, let's say, the semi-final version of the book, but the same URL will also host the final version of the book once it is ready, you know. This course, you know, it's, we will be happy to make it interactive. So, you know, when you have questions, just, you know, ask through the, by raising your hand. Okay, so again, what is learning to quantify? So in order to give you, can you please close your microphones, you know, in case you don't have questions. Thank you all. So what is learning to quantify? Here we have an example from, you know, a paper that was published, you know, 10 years ago, from a paper from computational social scientists, you know. So in computational social science, there are lots of these kinds of research, you know, in which social science is attacked from a computational angle by drawing data from typically from microblogs, from Twitter, from blogs, you know, drawing data from the data which are, let's say, already available on the web. Okay, so in this paper, the authors basically set out to understand or to plot, you know, the happiness patterns of the US population through 2010 and 2011 on a day-to-day basis, you know. So essentially what they did is, let's say, they downloaded all tweets that, you know, had to do with feelings and feelings of happiness, of sadness, etc. You know, tweets that were emotionally charged, you know, and they performed a sort of a sentiment analysis on each of them, trying to understand whether a given tweet displayed happiness, let's say a positive emotional feeling on the part of the tweeter, or a negative emotional feeling, sadness or something like that. Okay. And, you know, after classifying each of these tweets, essentially they counted how many positive tweets we had, how many negative tweets we had, and they plotted you know, the resulting, actually they plot the results according to a temporal time frame, you know. And here, for instance, we can see that, you know, this plot gives different colors to Mondays that are red, to Fridays that are pale blue, to Thursdays which are white, let's say that are yellow, etc. And so we can see a number of, so these researchers actually uncovered a number of patterns that were of interest, you know, to social scientists dealing with these matters. You know? So, for instance, they found out that, you know, people had peaks of happiness, you know, for specific, you know, specific days, you know, such as Valentine's Day or Thanksgiving, and specific and peaks of negative feeling for other specific days, such as Japan earthquake or the death of Amy Winehouse, etc. So, I mean, a number of patterns that you might essentially relate to emerge from this study. I want to plot a similar, sorry. I don't know what's happening with my slides. Okay. Okay, a similar aspect emerged here. Okay, so in this was a different study. This is one of the kind of plots that typically, let's say, get displayed on news portals during at election time. Okay, so this was from a national, from a portal of national news in Italy, and had to do with political elections. Okay, so this was the time of political elections in 2012, I believe, and so these plots actually plotted for 6 major candidates in the political elections. You know, they plotted the amount of negative mentions that these people received in microblogs. Okay, so you might see that, say, candidate Berlusconi managed to peak, to get, say, a peak of negative mentions about 5 February due to, you know, to something that I can't recall, you know. So, in essence, what does this plot have in common with the previous one? There are 2 important commonalities that I want to address. Okay, so the fact that in order to generate these plots, you know, people took a number of individual texts, microblogs, and classified them. You know, so here, you know, each microblog, each, let's say, tweet was the result, was subjected to a kind of sentiment classification. And here you're seeing only the tweets that were classified as having a negative polarity, you know. And similar in the previous image, again, we had some sort of binary classification, happiness versus not happiness. You know, that, and the results, you know, were actually plotted by counting the number of positives and counting the number of negatives. So these are characteristics that are common to these 2 studies, you know. And another commonality between these studies is that essentially none of the people who ran this study were interested in whether a specific individual had a positive or a negative feeling towards a candidate, you know, or a positive or a negative feeling towards his or her day, you know. They were interested only in the aggregate results, you know. And this is what, these are the 2 main characteristics of learning to quantify or quantification. So you might, in a sense, see techniques for learning to quantify as specialized classification techniques. Okay, so classification techniques which are specialized to the case in which our real goal is to figuring out not which, but how many. How many tweets, how many individual data points have a certain class label. So indeed, there are many applications of classification in which this real goal is determining what we call the prevalence of each class in the unlabeled data, or the relative frequency. So relative frequency is, terminology which is typical, say, of information retrieval. Prevalence is the terminology which is typical of, say, statistics. Okay, but we understand what it means. The ratio between the number of items that belong to a certain class and the total number of items in the class. Okay, so when this is the goal, our task is quantification, which is sometimes also called learning to quantify, supervised prevalence estimation, etc. So example questions that require addressing by quantification are, say, among this week's tweets concerning the next presidential election, what is the percentage of pro-Democrat ones? Again, here you see that there is a need of classifying items, because it's we don't know for certain whether a certain tweet is pro-Democrat or pro-Republican, and we are not interested in the individual tweet, but we are interested in the percentage. Another example is among this week's posts about the Apple Watch Ultra posted on forums, what is the percentage of very negative ones? Okay, so the previous example, pro-Democrat versus pro-Republican, is a typical case of binary quantification. Here we are talking about very negative, where probably the set of classes are, say, very positive, neutral, negative, very negative. And this is, what people call ordinal quantification. How are these percentages evolving over time? Okay, so here you're seeing an important aspect of quantification. Quantification is often used in order to monitor the evolution of percentages across a temporal axis. Okay, so monitor how support to Democrat evolves, maybe as a result of specific decisions taken by the Democrats, etc. So quantification is essentially a task that has been studied within different fields, machine learning, data mining, NLP, also IR to some extent, And what is important is that it has given rise to learning methods and evaluation measures which are specific to it. So we have learning methods which are for quantification, not for classification. Evaluation measures which are specific to quantification. So they are independent of those, say, of those for classification, which is a task which is closest to it. So it makes sense that because we have specific learning methods, because we have specific evaluation measures, we consider quantification as a task in its own right. Quantification is still a fairly unknown task among potential users. Okay, so there are many people who, let's say, would benefit from quantification, if they knew that there are specific algorithms for dealing with it. Okay, so many people, say in the social science, still use, the very naive algorithm for doing quantification, which is what we call classify and count. Classify every individual item and count how many items have been assigned a certain label. This is essentially the naive algorithm that all let's say, legitimate quantification algorithms strive to beat. So quantification, we have said that it has a reason in different fields, has been studied in different fields, And so it's not surprising that it goes under different names. Okay, so typically people who are in statistics, epidemiology, social science, etc., call it prevalence estimation. Machine learning people tend to call it class prior estimation, or simply prior estimation, you know, while people from data mining, text mining, IR tend to call it quantification. We will stick to the name quantification or learning to quantify, you know, for ease of explanation. And again, also there is some variability through the literature on the term of relative frequency, on what quantification deals with. Quantification deals with the estimation of the relative frequencies of classes, but which are also called the prevalence values of classes. So prevalence, the notion of prevalence is typical terminology from statistics, while the same, you know, is also called a priori probability, prior probability, or simply prior. And this is typical terminology from machine learning. So also there are slight differences among different fields, you know, in the kind of slant that these disciplines give to this study. So for instance, in statistics and data mining, which is the angle that we will typically use here, you know, the task is of independent interest. Okay, so there are applications where the relative frequencies or the prevalence values are what we are interested in. Instead, you know, in machine learning, this is often seen as an ancillary task. So a task which is essentially functional to generating better classifiers. So it's a stepping stone in order, so it's an intermediate phase of the problem of generating better classifiers for specific situations that we will talk about. So let me give you a brief overview of the structure of this course. So we will essentially introduce basic concept first. And second, we will look at some of the major applications of quantification in data mining, in natural language processing, and in machine learning. In the third part, we will look at evaluation measures. How should we evaluate the accuracy of quantification systems? And I'm speaking of evaluation measures in evaluation protocols, because we need the evaluation protocols in order to generate data sets for use in testing quantification. So parts 1, 2, and 3 will be the subject of today's talk. I'm not really sure whether I will be able to cover all of them. Instead, part 4, which will be given by Alejandro, will be the core part of this tutorial, of this course, and will have to do with the supervised learning methods for approaching quantification. And also a hands-on session will be provided in which Alejandro will show you, by using a library, a Python library that we have recently developed, how to set up quantification systems and evaluate them. If time allows, we'll have a session on advanced topics at the end. Okay, again on the theme of what is quantification. Quantification, we have defined it as the task of estimating the relative frequencies of classes, which also says that, in a sense, it can also be defined as the task of approximating a true distribution via a predicted distribution. So here we have a histogram in front of you, and so you might imagine these to be, say, a histogram that depicts let's say, the product reviews, or let's say the textual comments that have been posted on blogs concerning, say, the Harry Potter saga, you know. And so some of the reviews or the comments are very negative, some are negative, some are very positive. So this is an ordinal kind of quantification task. So the blue bars represent the true distribution, the gold distribution. So the distribution we don't know, that we want to approximate, And the red bars represent the predictions as returned by a quantification system. Okay, so you may notice that essentially the perfectly accurate system is the one where each blue bar is identical to the corresponding red bar. Here we have an imperfect quantification system that sometimes over-predicts the class. So this is the case of very positive, and in some other cases, it under-predicts the prevalence value of the class. And this is the case, for instance, of the positive ones. So you can notice that essentially we may view quantification as in terms of distributions, the presence of a true distribution and the attempt to approximate this by returning a predicted distribution. As a result, the evaluation measures for quantification will evaluate how well a predicted distribution approximates the true distribution. So we will confront with evaluation measures that compare two distributions. Why do we need to perform quantification? Well, essentially, one of the reasons why we want to perform quantification is that there is the phenomenon so-called dataset shift. So you may have heard of it already. Data shift is the phenomenon according to which in a number of application contexts, we have a discrepancy between the joint distribution of the two random variables x and y that represents the features or the covariates, x representing the features of the covariates, y representing the class label, the output variable. So a discrepancy between the joint distribution of x and y in the labeled training set, which we here indicate as L, and the same distribution in the unlabeled set that we want to quantify upon, we want to issue prediction for, a set that we here indicate as U. So when there is such a distribution, when there is such a discrepancy, we say that we are in the presence of dataset shift. So this plot is let's say a visualization of the fact that in this context there is indeed the dataset shift. So this is the result of let's say of analyzing the data in the RCV1 V2 datasets. It's called Reuters Corpus Volume 1 version 2. So it's a well-known dataset of news issued by Reuters and which are classified, were manually classified by editors. So this is one specific label called E21. I can't recall what it stands for, but so it doesn't matter. What it matters is that the data in the Reuters Corpus Volume 1 are 1 year worth of news, 52 weeks. And so this is what you see on the x-axis, okay? So on the x-axis, you see the data from the different weeks. On the y-axis, you can see the prevalence, the relative frequency of the class in the data. The blue plot indicates the true frequency. So what you can see is that, as it is pretty normal in many application contexts, the prevalence of the class fluctuates over time, and our application might simply consist in trying to predict, predict these class prevalence values and predict these fluctuations, So the red, yellow, and green plots actually indicate instead the results of applying 3 different quantification prediction algorithms to these data. And of course, I mean, the plot which can approximate the curve, which can approximate the blue curve better, is the better one, which is in this case the red one. So if in this case you see that there is dataset shift, but if we knew that there is no dataset shift, we could simply use trivial quantification systems such as the classify and count, or even the so-called maximum likelihood prevalence estimator. So the MLPE is the trivial rule that say, assume that in your data, the prevalence of the class is always the same prevalence that you saw in the training data, So of course, if there are no fluctuations, this is always correct, but, real data fluctuate, real data have some level of shift, So this is one of the reasons why we do need quantification systems. So why do we have dataset shift? Dataset shift may derive from different causes, different reasons. Okay, so one of the causes might be that the environment is not stationary across time and across space, across other variables. Okay, and so what do we mean when the environment is not stationary? Suppose that we are talking about news, news on a news portal, and one of our classes is terrorism, So we want to find out if how many, what is the percentage of news on the portal which are related to terrorism. Of course, when we had September 11, well, in August 11, the news related to terrorism were very few. But in September, and in October of 2001, the news on the very same portal were many more, So in this, we can see that the environment is not stationary with respect to the class labels that we are using, And this may be across time, but also we might have shifts that have to do with different regions in space in which these different geographical regions from which the data originate, or other variables. So in general, we say that the operating conditions are irreproducible at training time. So the conditions in which you operate, say the October 2001 conditions, were not reproduced at training time if the training data were August 2011. So you cannot always predict what the operating conditions in the future will be. Another type of cause for data shift is sample selection bias. Okay, so sample selection bias means that we know, so the way that we select our data for training, the way we select our training data is such that this training data cannot be representative of the operating conditions. So there is, for instance, there is an explicit way of introducing sample selection bias. So for instance, it's when, say, we need to oversample the minority class because we have too few examples from the minority class. Say we want to build a classifier for a rare disease, a disease that occurs, say, in 1 in a million patients. Okay, so if our training data are patient records, we certainly cannot have a training set consisting of 1 positive example and 1 million negative examples. So we need to oversample the minority class. We need to undersample the majority class. So in this case, the process of labeling the training data has explicitly introduced bias, has knowingly introduced bias. There is another case. So a case in which the process of labeling the training data implicitly introduces bias in the training data, because the technique that we use is a technique that generates biased training sets, say typically active learning. Okay, active learning, is such that the documents, the items that are selected for being part of the training set are anything but a random sample of the population, you know. So active learning implicitly introduces sample selection bias, you know. So, you know, there are many different, many positive, many different possible causes for dataset shift. But the commonality between all of these causes is that the presence of dataset shift invalidates the IID assumption, the assumption according to which the training data and the unlabeled data on which we want to apply our predictor, you know, are sampled independently and are sampled independently from the same distribution, identically and independently from the same distribution. And on the IID assumption is an assumption which underlies all standard machine learning algorithms. So this means that using, say, a classify and count algorithm, which is based on this assumption, you know, may lead to a quantification accuracy that is not optimal and that is indeed actually poor, you know. So again, on dataset shift, in quantification, what we are actually interested in is in detecting whether there has been a shift in PY, in the distribution of the class label. This is indeed the goal of quantification, you know. And so we should actually distinguish a number of cases in which PY can evolve, you know. Actually, this what I'm seeing, what I'm discussing in this slide is you know, still a matter, is not something which is already settled in the literature. There is still a lot of discussion on these concepts, but I'll try to give you an idea of some important concepts. Okay. So a number of authors actually distinguish prediction problems in two classes. Okay, so prediction problems where we have a label Y that needs to be predicted based on a vector X of features or covariates. So features is a typical terminology of machine learning, covariates is the typical terminology of statistics. And a number of authors distinguish these problems into two classes. Y implies X problems and X implies Y problems. So in Y implies X problems, you know, these are the problems where the class probabilistically determines the covariates. Okay, so the class probably determines the distribution of the covariates. So one example is think of handwritten digit recognition. Okay, so you need to recognize digits from 0 to 9, handwritten one, you know, based on the graphical features with which these digits have been written by hand. You know, a typical application, say, in the automation of surface mail. You know, in this case, well, we have 10 different classes, you know, which are the 10 different digits from 0 to 9, you know, and the covariates are, you know, characteristics of the graphical renditions of these digits, you know. Well, can you please? Can you all mute your microphone?
Keep being posted.
So you wanted to ask a question?
What?
We want you for the
Yeah.
Hi, you wanted to ask a question?
I think I should go in.
Bring a FFP to mask.
Should I go in there and say, guys, I'm grown?
Can you
wear your
please
mask normally?
And then I
Mauricio, I think you can mute
and I say,
them.
I have grown.
Yes.
Yeah?
Can you please mute your mic if you
No.
don't have questions to ask? Thank you. Okay, so I was speaking about Y implies X problems and written digit recognition, So this is a Y implies X problems because, the person who writes a digit, intends to write, say, a 0, and generates a rendition of it with certain characteristics. Okay, so the intention to write a digit in a certain class generates the features. Okay, so in this case, a typical factorization, which is mostly convenient for the joint distribution Pxy, is a factorization in terms of Px given y times Py. And in these problems, changes in Py do not depend on Px, okay? So this is something which is called the prior probability shift, So imagine imagine a practical case. We have a handwritten digit recognition system, which has been, say, trained on a training set of, digits from 0 to 1, but we now need to apply it on a set of unlabeled digits, where we know that these digits are binary, so just restricted to 0 and 1. So in this case, we have a significant change in Py, in the prevalence values of the different digits, and this doesn't depend on a change, in the covariates. So this is a classic Y implies X problem. And in this case, we speak of prior probability shift. Okay, so a change in the class prevalence values from training set to unlabeled set. A different type of problems is X implies Y problems. Okay, so in which the covariates probabilistically determine the class. So weather forecasting is a typical example. Okay, so in weather forecasting, we need to predict whether, say, it's going to rain or not. And the covariates are physical characteristics such as, humidity, wind, temperature, etc. So in this case, in these problems, changes in Py may be due to different reasons. Okay, so one typical case is changes in Px, but with Pyx being constant. Okay, so well, in this case, maybe you have trained the system to predict rain in one region, and you want to apply it in a different region where typical conditions in humidity, in wind, in temperature are different. But Pyx tends to be constant. Okay, so the laws that determine, the physical laws that determine, when it rains or not, tend to be constant. In this case, we speak about covariate shift, And a different case is when we have changes in Pyx with Px remaining constant. This is a very difficult case. This is called concept shift. And why do I say that it's difficult? Well, because the Pyx changes, because let's say, the functional relationship that links the class label to the covariates has changed. So here, this raises problems of learnability, So indeed, conscious shift is the most difficult type of shift. It's not something that we are going to address today. So today, and in this course, we are going to address prior probability shift and covariate shift. And typically, we will mostly address prior probability shift because quantification has mostly paid attention to prior probability shift, So it's still true, that research on the relationship between quantification and, say, covariate shift is still a bit lacking for reasons that we will discuss in the rest of the course, So here you can see a visualization, of different types of dataset shift, So here this is an illustration taken from a previous paper by other authors, in which you can notice that these authors use the term concept drift. Okay, so shift and drift tend to be used interchangeably in the literature. Okay, so in the top left plot, you can see a distribution of the training data. Here we are actually witnessing a case of regression, not of classification, because you can see that the y-axis displays values from 0 to 1, and we are witnessing a case, let's say, a univariate regression. So we assume that there is a single covariate, which takes values between 0 and 1. So the top left panel indicates training data, Let's look at the top right panel. So here we have the unlabeled data represented by red circles, and we see that the distribution is pretty similar to the one in the training data, So we have no prior probability shift, no concept shift, no shift whatever, Here, again, there is a change in terminology. You can see that these authors speak of distribution shift, where we are going to speak of prior probability shift. Again, a sign that terminology is still variable across the literature. Let's look at the panel on the bottom left. Here, we are in the presence of prior probability shift, because you can see that let's say the functional relationships between y and x tends to be the same, but it's simply that the covariates have shifted. So we now have, so the unlabeled data, are mostly data where the value of x is between 0.4 and 0.8, instead of being between 0.0 and 0.6 as in the training data. So here we have prior probability shift, but no concept drift. Okay. So instead, in the bottom right image, the situation is completely different. So you can see that, the covariates, the covariates have remained the same, so we are still in the presence of data where the value of x is between 0 and 0.6, but the functional relationship between x and y has changed a lot, And this is the case of concept shift that I said, is the most difficult cases, the most difficult case in data shift, and that we are not going to tackle in this course. So just to sum up, differences between classification and quantification. In classification, we are given a training set of labeled data points, xi, yi, I, and we need to train a classifier that is a function function h that, given an example in x, returns a label in y. Instead, in quantification, we are still given a training set of labeled data points like in classification, but the goal is to train a quantifier. A quantifier is, is a predictor that takes as input a set of data points and returns what? A class distribution, which is here indicated by this symbol that represents the probability simplex. Okay, so essentially, take a set of data points, return a distribution across the classes in Y, And again, in classification, the prediction is HX, it's Y, which is here indicated with a hat. Hat indicates estimation, Hat Y, which is HX, is a data point, and Hat Y is a class label. Instead, in quantification, you have Q sigma, we indicate with sigma a sample of data points. So the application of a quantifier to the sample returns what? Returns a distribution over y, a predicted distribution. Okay, so we indicate with P a distribution, and we hat P the prediction, the estimation of the distribution. So the type of error that we do for classification are, say, one error is we take a data point and we misclassify it. The error that we do in quantification is instead, for a given class, we either underestimate or overestimate its prevalence values. In classification, in standard classification, we work by assuming that the IID assumption holds. In quantification, we do exactly the opposite, because quantification, so if we assume that the IID assumption is true, well, quantification is trivial, So in quantification, we assume that we have dataset shift. And this assumption is something that we encode in the evaluation protocols that we use. So you will see that we essentially test our quantification systems on datasets that exhibit dataset shift, because this dataset shift has been built into these datasets by the evaluation protocol, and we will come to it. So let's speak of classify and count. So classify and count is the, let's say, the trivial algorithm for doing quantification. The one that consists of, let's say, classifying all the items in the sample, and then counting the number for each class, counting the number of items that has been assigned to the class, and then dividing by the total number of items in order to compute the relative frequency. So this is the classify and count algorithm. Is this the optimal quantification strategy? No. So the answer is no. Well, this is a bit surprising in the beginning, because we often say, if we have a perfect classifier, this is also, of course, a perfect quantifier, so a perfect estimator of class prevalence. The problem is that a good classifier is not necessarily a good quantifier, and vice versa. And I'll show you an example why. So let's look at this example. So here we have two different classifiers, H1 and H2. We apply them on a certain test set, and we see that H1 makes 5 false positives and 20 false negatives. H2 instead makes 20 false positives and 20 false negatives. So which classifier is better? Of course, H1 is a better classifier than H2 because it does 25 mistakes instead of 40 mistakes. Which one is the better quantifier? Which one is the better estimator of the positive class? It's H2. It's H2 because, if we, for the goals of quantification, making a false positive and a false negative, they cancel each other out, because a false positive say, well, no, the class, this item doesn't belong to this class, while it should have been, and the other says, well, the document belongs to the class, while it shouldn't be, So a false positive and a false negative, their combined effect, it amounts to 0, So H2 is a better quantifier than H1. So this shows that quantification and classification cannot be seen as the same task, So you cannot see quantification as a byproduct of classification, because classification pursues different goals with respect to quantification. Here we say that classifier H1 is biased, Biased in the terminology of quantification means a classifier that has a tendency to make more false negatives than false positives, or more false positives than false negatives, okay? So while a non-biased classifier is one that tends to make the same amount of false positives and false negatives. So indeed, this is a bit of a paradox of quantification. So we should prefer a classifier that makes more examples, provided it makes them in a more balanced way, So in a sense, the impetus behind the research on quantification has had two main reasons. Okay, so to fight classifier bias, to deal with the fact that classifiers may be biased, that even when, say, you train a support vector machine, you optimize the parameters, etc. The optimal classifier that you might generate from a training data may be biased. So, as I was saying, the impetus behind quantification research, had two main reasons. Dealing with the presence of classifier bias and dealing with the presence of dataset shift. I'll show you in a practical way, how classifying count delivers bias results. Here in front of you, you have what in quantification is called the diagonal plot. So a diagonal plot consists of the following. So we take a quantification system. We provide the quantification system with a number of unlabeled sets, a number of test sets, a number of test samples, characterized by different gold prevalence values, and we ask it to predict the prevalence, and we plot the result in this diagram. Okay, so you might notice that the dashed line, which runs on the diagonal, represents the ideal performance of a quantification system. Because, for instance, when the true prevalence of a given sample is 0.4, the quantifier predicts exactly 0.4. When the prevalence is 0.8, it exactly predicts 0.8. So we plot the results of quantification systems on these diagonal plots, and the closer the plot that represents a given quantifier comes to the diagonal, the better. So this is an example, of a classify and count system which we had trained on real data, and it shows the performance it delivers. Here we call it CC 50% because the training data that we used for training the classifier contained exactly 50% of positive examples, 50% of negative examples. So you might notice that this classify and count quantifier performs suboptimally, in the sense that it performs very well when we provide it, with unlabeled samples that have a prevalence of about 0.50, it returns a perfect estimate. But as soon as the true prevalence gets away from 0.50, we have either, a problem of underestimation. So like in this case, so the system should have predicted 0.8, but it predicted 0.7, or a problem of underestimation, of overestimation. So we should have predicted 0.2 for the positive class. Instead, the prediction was around 0.25, 0.30, So you might notice that here the classify and count system is a bit biased, towards the prevalence of the training data, the prevalence of the class that was found in the data used for training it. And this is no accident. Okay, so what typically happens is that when you ask a classify and count system to predict a certain percentage, you know, like here. So it will tend to predict a percentage which is somehow intermediate between the true percentage, 0.8, and the percentage of that the class had in the training data that was used for training the classifier, which is 50. So something which is intermediate between 50 and between 80, you know. And you can notice this, you know, this is the same classifying count system run on different training data, you know. For instance, CC 10%, which is this plot, you know, is a classifying count system trained on training data that contained only 10% of negatives. And you can notice that this classifying count system tends to systematically underestimate the positive class. While the opposite case is CC 90%. So here we had 90% of positives. So this classifying count system tends to systematically over-predict the true prevalence case. Okay, so I believe that you know, these results, you know, when people see these results, this often comes as a shock to many, you know, because, you know, people say in computational social science say, well, you know, I've always used, you know, when I wanted to make my let's say, my estimates of class prevalences, I've always used, you know, the best possible classification technology, you know, and I had always thought that, you know, these delivered very reasonable results, you know, and I wouldn't have imagined, you know, that you might run in discrepancies between, say, a gold prediction, let's say a gold prevalence of 0.2 resulting in a predicted prevalence of 0.75, you know. This is fairly shocking, you know, but this is the hard reality of data, you know. So classify and count is not a good way to do prevalence prediction. Instead, you know, here you might, you see three different systems compared. Again, we have our classify and count trained on 50% of the data, you know, and on the same data, we have two different quantification systems, HDY and EMQ. So these are two systems, two important systems that Alejandro will discuss in the next class. And you can see that their curve mirror much better the ideal quantification system. You know? So you can see that, you know, there is a point in studying quantification systems here. So we have seen that classify and count delivers biased results. Why does it deliver biased results? Well, you know, there are many different reasons depending on the different learning algorithms. I'm showing you here an example coming from probabilistic classifier, and specifically from the optimal Bayes classifier, which has the mathematical form that you see in equation 1. Let's read it. Essentially, it says that the probability that item X has class Y, in order to estimate this probability, we should, you know, just by an application of Bayes' theorem, this is equivalent to the probability that the probability in U, in the unlabeled data, of X given Y. It means the probability that if we pick at random an example that has label Y, then it has the vector of covariates is indeed vector X, multiplied by the probability in U of Y, which means the class prevalence value of Y in U, divided by the probability in U of vector X, okay? So if we want to compute this probability, we have a problem, So these two things, PU x given y and PU y, are unknown because we don't have access to the labels of the unlabeled set. So we need to estimate them on the training set. So we make to replace U with L, So the estimation basically conducts us to replacing PU x given y with PL of x given y, where L is the training data, and PUY with PLY. Okay, so if we want to estimate the probability of y given x, we do this replacement. And this will also allow us to estimate PU given y, to estimate the probability, let's say the class prevalence of y in U, as the sum of these probabilities. Okay, so that's good, So this is the standard estimation we do, when we train Bayesian classifiers, and essentially this is the same that we do for training the naive Bayes classifier. There is a problem though, So we assume, this development we did assumes that PL is a good estimate of PU, of PUI, okay? Is it a good estimate? Sure, it is a good estimate when we don't have dataset shift. But if we are in the presence of a shift in the class prevalences of Y, say there is prior probability shift, then PUY, so the frequency of class Y in the unlabeled data is very different from PLY. So this estimate is inaccurate, It's inaccurate. So if PLY is much bigger than PUY, these probabilities will be overestimated, and this class prevalence value will be overestimated. This is essentially the very same phenomenon we saw here. Okay, so this is an example of why classifying count may deliver biased results in the case of Bayesian classifiers, but similar cases obtained for other learners. So quantification as a discipline, has evolved in a highly nonlinear way. It's essentially a task which has been discovered and rediscovered within different disciplines. Okay, so there was a first stage of interest in this task within machine learning. As I said, in machine learning, there was this problem, estimating class priors, estimating prior probabilities, prevalence values in data which were not IID, in data characterized by dataset shift. And why was this interest? Well, the interest on the part of machine learning research was to make classifiers robust to the presence of prior probability shift. So to improve classifiers when for use on datasets, on datasets characterized by prior probability shift. Indeed, in this case, if we have the optimal Bayes classifier, if we can estimate, if we can estimate PUI better than by simply replacing PUI with PLY, if we can do quantification, say, estimate PUI, we can replace PLY with a better estimate, and which means make a better probabilistic classifier, So this was the main interest on the part of machine learning people. So, and this trend started at the beginning of the year 2000, and the most influential work is this paper by Marco Serens and colleagues, adjusting the outputs of a classifier to new a priori probabilities. And this indicates the SLD algorithm, or also called EMQ sometimes, which is an algorithm that Alejandro will explain to you. So there is a second stage of in the history of quantification research. So it was interest in this task by data mining and text mining people, So here the goal was not improving a classifier, but was indeed estimating quantities and trends, So here you can see an important difference, okay? So in data mining, in text mining, class prevalence values have an independent interest, So as when, we want to establish, the proportion of tweets that, support a given political candidate. So there is independent interest in this. In machine learning, instead, in the previous phase, there was not any independent interest in the class priors. The class priors were only interesting since they allowed to improve classifiers. So it is indeed the applications that from data mining and text mining that have provided the impetus behind the most, this recent wave of research in quantification. And the very recent wave on research in quantification, I would say in the very few last years, also has to do with the renewed interest in dataset shift. There is much more research nowadays than 10 years ago on dataset shift, on different types of dataset shift. And so there is now interest in trying to, specialize quantification to different types of dataset shift. So there are a number of tasks in data science which are a bit reminiscent of quantification, but are different. Okay, so quantification is also reminiscent of something which is called prevalence estimation from screening tests in epidemiology. And what is a screening test? In epidemiology, it is a test that a certain patient undergoes in order to check if the patient has a given pathology. Say a test that tests you for HIV, And these tests are often used for epidemiological purposes, So when they are administered to a certain population, their goal is to figure out, say, what is the prevalence of HIV, whether the prevalence of HIV is increasing, whether it's spreading to a different geographical region, etc. Well, these tests are, the problem is that they are often imperfect, as classifiers. So they may generate either false positives or false negatives, okay? So a false positive is that when a patient is incorrectly diagnosed as having the pathology, while a false negative is when a patient is incorrectly diagnosed to be free from the pathology, So this is very much akin to classification, The differences between a screening test and a supervised classifier is that in a screening test, of course, there is no supervised learning, and also the fact that a screening test typically has known and fairly constant sensitivity and specificity. Sensitivity is the term that the medical field uses for recall, and specificity is the term that the medical field uses for 1 minus fallout. Okay, so it's essentially recall on the negatives. So the same doesn't usually hold for a classifier. Okay, so a classifier doesn't have constant precision recall. And so there are indeed differences, but there are also similarities. And indeed, the similarities are such that some of the currently used quantification methods indeed derive from methods that were used for prevalence estimation from screening tests. We even often study or use a quantification method called ACC, adjusted classifying count, which the people in epidemiology used as far back as 1966 or something like that. Another discipline which is fairly similar, is density estimation. Density estimation is, say, the task of a typical example is estimating the prevalence of yellow balls in a large urn containing colored balls. So this is an example, a textbook example of density estimation. What are the differences? Well, in traditional density estimation, the problem is that we can deterministically assess, whether each item belongs to the class, So in our machine learning terms, we could say that variable yj can be observed. Okay? So we can, if we extract a ball, we can immediately, and we certainly say that this is a yellow ball or that this is a red ball. In classification, in quantification, this doesn't hold. We need a process, of figuring out the class label of the individual. And the second difference is that in traditional density estimation, it is either impossible or economically implausible, to assess class membership for each individual item, So when we have a large urn of balls, we do not want to inspect every single ball in the urn. When we have a large population of patients, we don't want to test each patient in the population. We want to do estimates. Okay. In quantification, this is not true. Because in quantification we deal with digital objects that can be, managed in the millions. Okay. So we don't have mechanical processes. So there are indeed differences between density estimation and quantification. So quantification is certainly more closely related to classification, where the two previous properties do not hold. The difference is that, of course, in classification, the goal is correctly estimating the true class of each single individual. So quantification concerned not with the needle, but with characterizing the haystack, and also the fact that classification is applied to individual items and not to sets, not to batches of such examples. Well, batches that we call actually samples in quantification terminology. Yet a different, similar task, collective classification. Well, collective classification is, say, one example is classification of network items. So you need to classify, people who have Facebook accounts, and one feature that you can use in this classification is the fact that there are links between these people. In Facebook, I have friends who are other people that I want to classify. So similarly to quantification, in collective classification, the classification of a single data point is not viewed in isolation of the other data points. But the focus is quite different. In collective classification, we are only interested in improving the accuracy of classification by exploiting the links, by exploiting the relationships between the data points to classify. So in collective classification, our interest is still at the individual level and not at the aggregate level as in quantification. Okay, so I think, well, this basically finishes the introduction. So this may be a good moment to ask questions if you have questions. If you want to, someone wants to raise your hand. Okay, unless I see raised hands, I'll carry on, and I'll start to introduce, to discuss a bit the applications of quantification. Okay, as I said in the introduction, there are many fields of human activity which are not concerned with individual data. So these fields are concerned with aggregate data only, with percentages of individuals, percentages of data points in a population, where the population is often broken down according to variables, which may be age group, gender, religion, job type, geographical region, organization, you name it. Okay, So examples of these applications are the social sciences, political science, which is often seen as a sort of a subset of the social sciences, epidemiology, market research, ecological modeling, and the like, So essentially, you see, if you look at research papers in this area, many research papers use nowadays, use machine learning of some form, on some form of data, and it is often invariably the case, that when they use classification technology, what they probably meant was, quantification. What they probably would have benefit for was, proper quantification algorithms, because these disciplines are inherently interested in the aggregate level, Let's speak about the social sciences. Okay, so we have seen one example in the early slides, the happiness study. The happiness study is, a sort of a paradigmatic example of this big new paradigm that has swept the social sciences and which has been spurred by the availability of big data from social networks. Okay, so in the past, the social sciences used to work by gathering data from surveys, from interviewing subjects. The problem is that since the advent of social networks, okay, so the advent of platforms where the subjects that social sciences study, let's say, generate data by themselves, it becomes very attractive to use this kind of data instead of eliciting them, for a number of different reasons, okay, because these data have been generated spontaneously, which is different from the data that you elicit by a survey, So computational social science basically adopts this kind of paradigm. So the data that we social scientists need are there, are there already without the need for eliciting them, and are there in the social science platforms, And so indeed, within the social sciences, the individual data points on which we perform quantification are real people, represent real people. So, and here we have different quantification endeavors. So one typical application is quantification by topic. Say, we want to establish the prevalence of a certain topical class within respondents of a certain survey, or within owners of Facebook accounts, etc. Sentiment quantification, sentiment quantification is probably the biggest one here, So the goal of many works, that do sentiment classification, say, of Twitter data, is estimating class prevalences, So can you think, of an application where we want to classify tweets by sentiment because we are interested in the sentiment of a specific account holder? I cannot, Typically, when we want to classify tweets by sentiment is because we are interested in Twitter because it's a large data set, It's a large data set on which to run statistics. And because of this, we are not actually interested in classification, we are interested in quantification. Stance quantification is a sort of a variant of sentiment quantification. And here has to do with detecting the prevalence of individuals that have a certain stance, that have a certain position towards a given issue or topic or target. So this involves actually analyzing the text and detecting whether the opinion which is expressed there is an indeed opinion about the given target. As I said, political science is very much a variant of social sciences, you know, and here you can probably imagine the applicative potential of quantification, say in predicting election results or monitoring support for a political party by estimating class prevalences for support or for contrariety in blog posts, you know. And again, you know, stance quantification is of critical importance within political sciences. As I said, interestingly enough, you know, if you look at the literature of computational social science or computational political science, most works in these fields still use classify and count. And the reason why they use classify and count is their lack of awareness that there exist alternative quantification methods, and probably their lack of awareness that there exists a task, a data science task called quantification. So an example for the social science is this plot. Okay, you can see many such plots in this computational social sciences paper. Here, this paper was about the Arab Springs in Egypt, and this displays the temporal trend in the proportions of tweets that support or oppose the military intervention in Egypt. So you can see that there is a large amount of shift, you know, and because shift exists, you know, shift happens, as someone has said, you know, because shift happens, you know, quantification is needed. Ecological modeling, a similar problem. So here, so this plot is drawn from a paper from people who used quantification for estimating the prevalence of different species, different natural species of living beings on the seabed, you know. And of course, I mean, they had the training data. The problem is that the training data they had been obtained, you know, there essentially were photographs of the seabed, had been collected and then annotated, you know, from photographs taken in some geographical areas. And these people wanted to then apply, you know, these, the quantifiers that they had trained. They wanted to apply it to images obtained on other geographical areas. So this is typically a case of a prior probability shift, you know, because in these different geographical areas, different living species existed, you know. So here is a display of the results, you know, that this study obtains, you know, where each different column is a different sample. You might imagine it being a different image, you know, and the different bars represent the different living species, you know. And you can notice, you know, that there is a wide amount of variability between different samples collected in different geographical areas, you know. Market research is very similar, you know, is another application where in market research, essentially what you do is you try to estimate the distribution of the attitudes of consumers about products, attitudes about product features, marketing strategies, etc. So typically this might involve classification or let's say supervised learning, because sometimes, you know, if you want to estimate this distribution, your data may be, say, verbal responses to surveys, you know. So you need to classify text, or better, you need to quantify text, because if your question is, say, when McDonald's is interested in figuring out whether customers, you know, like onions in their cheeseburgers, of course, you know, McDonald's is not interested in the fact that John Williams likes onions, you know, in cheeseburgers. McDonald's is interested in the population at large. So this is quantification, it's not classification. Epidemiology, again, as I said, you know, epidemiologists are the only type of medical personnel who are not interested in the individual patients. They want to track the incidence and the spread of diseases. Say estimate pathology prevalence from clinical reports where the pathologies are diagnosed. And one interesting fact is doing epidemiology by verbal autopsies. A verbal autopsy is a verbal description of the symptoms, that a dead patient, a diseased patient, the symptoms that it had just before dying. So if this is a verbal description, it requires classification. If the goal is epidemiology, then it requires quantification. Just to finish, other applications are, say, natural language processing and machine learning. In natural language processing, those of you who are in NLP know about word sense disambiguation. Word sense disambiguation basically means I find a certain word in a sentence. I need to decide, in which sense this word is used. Say, I find the word bank in a certain sentence. I need to figure out whether bank here means a financial institution or something like the river bank, whether it means a hydraulic artifact and a hydraulic engineering artifact. Okay, and indeed, the problem is that word sense disambiguation systems need to know the prevalence of the different senses in data. For instance, they know that bank in the financial sense is much more prevalent than in the hydraulic engineering sense. Well, the problem is that if you want to do domain adaptation, say, if you want to apply your word sense disambiguation on a corpus of, say, scientific articles about hydraulic engineering, then this prevalence is much different. So when you want to take a word sense disambiguator, you might want to tune it, to the domain where you want to apply it. And this domain is typically characterized by word sense prevalences or sense priors, as they are called, different from those of the training set. Again, I use for quantification. For machine learning, we already mentioned that the fact that the main rationale is estimating the class prevalence of the unlabeled set in order to improve the performance of classifiers, in situations which are not IID, in situations that are characterized by dataset shift. But the ones that I've mentioned are just the main applications of quantification. There are really scores, of different applications around, So for instance, some time ago, we worked for a project for a major airline, and this airline, wanted to predict the proportion of no-shows, within a set of bookings. Okay? Because when, let's say, when a passenger, say, has a booking and doesn't show up, that's a loss for the airline, because the flight leaves with empty seats, So the airline typically want to establish to predict the proportion of empty seats because they want to fill in these seats. They want to do overbooking, a phenomenon that is well known in airlines. Okay, so in this case, typically you might have a certain passenger, and this passenger might have a record, a record by which the airline might want to predict how probable it is that this passenger doesn't show up. But of course, the airline is not interested in the individual passenger, but is interested in how many passengers will not show up. So this is, again, a quantification. Lastly, for hematology, estimating the proportions of different types of cells in blood samples. So you might have a blood sample, an image of a blood sample where you want to classify each cell that you are able to individuate, to identify, to classify it as being, say, a white cell or a or a red cell, because if the percentage of white cell is excessive, then this is important in the diagnosis, say, of leukemia, And of course, this is a problem of quantification. You are not interested in individual cells, you are interested in how many. In general, we will draw many examples in this tutorial, in this course, from text classification. In text classification, you can perform a classification according to various dimensions, So this holds for text classification, but it holds for quantification as well. We have already mentioned that we might want to do quantification by topic and quantification by sentiment. Quantification by language is indeed very important, So you might want to classify or quantify, let's say, a certain population by mother tongue, say, in order to estimate language diversity within a certain population. In general, as I said, there are scores of applications of quantification in the literature, but they may be distinguished into applications that apply methods which were especially designed for quantification, and this is the minority, but the majority are applications that, unaware of the existence of specific methods for quantification, apply standard classification methods and classify and count. They optimize their SVM and they use classify and count, which is something which shouldn't be done, Let me use the last 20 minutes in order to go through evaluation measures and evaluation protocols, In order to discuss evaluation, we need to fix some terminology, As I mentioned, we'll think of quantifiers, as predictors that take a sample of data points, sample of items, sample of documents from a domain X, and that need to establish the class prevalence of each class in a set Y of classes. So sometimes the set of Y of classes, we call it the code frame. So, of course, like in classification, there are different brands of quantification. And let's go through the different types of classification we're interested in. So most of these notions you already know. So binary classification, in which each item has exactly one of two classes, which are Y1 and Y2. Single label multi-class classification, where each item has exactly one of n different classes, with n higher than 2. Multi-label multi-class classification. So in multi-label multi-class, each item may have any number of classes, 0, 1, or several, picked among n different classes, Y1, Yn, with n higher than 1. Typically, multi-label multi-class is, when we want to solve it, is often reduced to binary, by solving n independent binary classification problems or quantification problems. Indeed, we will not speak, maybe we will touch on multi-label, multi-class quantification in the advanced topics section of this tutorial. And then ordinal classification, which is also often called ordinal regression, you might know it under this name, is the case in which is the single label multi-class classification case in which the n classes have a total order defined on them, such as when you have a very negative, neutral, positive, very positive, And there is a total order between them. N is higher than 2, and the total order means that different mistakes are not maybe more serious or less serious. So mistaking very negative for very positive is much worse than mistaking positive for very positive. And then we have a metric regression, which is not a type of classification. This is the case in which each item has not a class, but has a real value score from a certain range, alpha, beta. So for each, here we have listed different types of classification, but for each brand of classification, for each type of classification we mentioned, here we will be interested in its quantification equivalent. So we will be interested in binary quantification, single label, multi-class quantification, ordinal quantification, and the like. Most of the discussion in this course will be framed in terms of single label, multi-class quantification. Why is this so? Well, for instance, because single label, multi-class quantification is probably one of the most general among these types, okay? Because binary classification is a special case of single label multi-class, because multi-label multi-class can be solved in terms of binary, which means in terms of SL-MC, and because, most of the research, on quantification to date has been carried out for single label multi-class. So there is very little research on ordinal quantification. There is very little research on multi-label multi-class, not to speak of metric, of quantification, the quantification equivalent of metric regression. So let's say unless we say something different, everything we will say in this course will have to do with single label multi-class classification or binary classification. So how do we evaluate quantification methods? Okay, as in all data science, essentially evaluating quantification means evaluating the accuracy of quantification, evaluating how well how accurately quantification does its job. And in the case of quantification, it means measuring how well a predicted probability distribution fits a true distribution, how well the predicted probabilistic distribution fits the unknown gold distribution. So here we note the gold distribution with PY and the predicted distribution with hat PY, where this hat accent indicates estimation. Okay, so in general, in the let's say in the quantification literature, our evaluation functions are not functions that measure quality, but functions that measure lack of quality, are functions of error, So they are functions that measure the quantification error. They are functions that measure the divergence, how a predicted probabilistic distribution diverges or is different from the true distribution that it was meant to approximate, And indeed, in mathematics, there are a number of functions that are called exactly divergence functions. A divergence function in mathematics is a function which has two parameters, and the two parameters are two probability distribution. And the function measures the divergence, the difference, the distance, between these two probability distribution, So a divergence function, all divergence functions, enjoy two properties, okay? So one property is the identity of indiscernibles. That says that if the function evaluates to 0, well, the function evaluates to 0 only if the two distributions are the same distribution, And the second property is non-negativity, which says that, all the values of the divergence function are higher, greater or equal to 0. So it means a divergence is a measure of error, okay, because it's 0 only for the ideal, for the perfect case, you know. Well, you know that if a divergence did enjoy also these two properties, it would be called the distance, you know. And these properties are symmetry, so it means that dpq implies dqp, you know, and the triangle inequality, you know, dpq plus dqr is greater or equal to dpr, you know. So if a divergence enjoys also these two properties, it's called a distance function. The problem is that we will not be terribly interested in symmetry and triangle inequality because these two properties are not essential for the purposes of quantification. So there is no reason to say that these properties are desirable. So for instance, one reason why symmetry is not necessarily desirable is that we are always comparing a predicted distribution to a true distribution. So if our divergence doesn't enjoy symmetry, in order to use it fruitfully, we only need to say, establish that the first argument is the predicted distribution and the second argument is the true distribution, or vice versa. So never exchange their roles. But we don't need symmetry, we don't need the triangle inequality. Instead, divergences, there are two other properties that may be interested in quantification that are called impartiality and relativity, you know. So impartiality is this property, you know, which is slightly clumsy to read, but let's say if we have, let's say, a predicted distribution, you know, such that let's say the predicted distribution underestimates py by a certain value a, and the second predicted distribution that instead overestimates the prevalence of the class by the same amount, then, you know, these two distributions evaluate to the same score, you know. We say that in this case, the divergence enjoys impartiality. So this property enforces the notion that underestimation and overestimation are equally serious. Let's say, if we have a divergence that enjoys impartiality, it means that, you know, so if the gold value, the true value of py is 0.20, well, estimating it as 0.10 or estimating it as 0.30 are equally serious mistakes. So underestimation and overestimation by the same amount should be equally penalized. If they are equally penalized, we say that the measure enjoys impartiality. Another property, interesting property, is relativity, you know. Here, this is even more clumsy to read, but I'll try to simply say it by examples. Okay, so relativity enforces the notion that estimation errors of the same absolute magnitude are more serious for rare classes, you know. So the idea is, suppose that you have, let's say, this the true prevalence is 0.02, you know, and your mistake, your quantifier evaluates it at 0.01, you know. And suppose that instead your true prevalence is 0.50 and your quantifier evaluates it at 0.49, you know. Which of these two mistakes are more serious? Is this mistake more serious than this mistake, or are they the same? You know, if this mistake is considered more serious than the other, we say that the property, that the divergence enjoys relativity because it enforces the notion that estimation errors of a given absolute magnitude are more serious for rare classes. Say, in this case, suppose that we are talking about estimating the prevalence of a rare disease, Well, if the true prevalence is 0.2 and your estimate is 0.1, well, you are estimating to be 50% less than it is, So this mistake is not really a tolerable mistake. But this mistake might be more tolerable, because we say, that from a relative point of view, 0.49 is not too different from 0.50. Okay, so if these two mistakes are considered equally serious, then the divergence doesn't enjoy relativity. If the second is less serious than this, then we say that the divergence enjoys relativity. So, given these properties, that might be desirable, might or might not be desirable, which evaluation function is more desirable? So a number of measures have been proposed in the literature, and the answer on which evaluation function is more desirable really depends on the application. So arguably, there are some applications for which relativity is desired, while some others it is not desired. So I'll give an example. So estimating the prevalences of illnesses in a given region, in a given age group. Here, relativity is desired, because of the example I gave earlier, a rare disease, for a rare disease, a 0.1 estimation error is tolerable if the true prevalence is 0.40. It's not tolerable if the prevalence is 0.0001, Instead, take another application, application 2, predicting the prevalence of no-shows on a flight-by-flight basis, Relativity is undesired here, because, a 0.02 estimation error has the same impact if let's say, if the true percentage is 0.5 or if the true percentage is 0.20, because, say, suppose that on the flight, there are 100 seats, and if PY 0.05, it means that the gold percentage, that there are the true number of people who don't show up will be 5. Here, there are going to be 20 people who don't show up. If you do a 0.2 estimation error, it means that you missed the goal by 2 people. Okay, so is it more important when in this case or in this other case? It's the same, because it's always 2 people. It's 2 tickets that you might have sold, or 2 tickets that you should have avoided to sell, So in this case, relativity is undesired. Instead, the other 3 properties that we discussed, identity of indiscernibles, non-negativity, and impartiality, are always desirable. Okay. I think I'll stop here. We are our time has ended. In the next class, I will finish discussing actual evaluation measures, and I will start discussing evaluation protocols, after which Alejandro will start presenting quantification methods. I guess it's again a good moment to ask if there are questions to ask. Are there any questions about the material that I have presented? Okay, there will be, if you think it over, maybe there will be opportunities in the next lesson, in the next lesson to ask questions even on aspects of this part that might have arisen. So just please let us know. Otherwise, we'll see you again in 2 days, same time. You will receive a Zoom link for next lesson. Okay? Thank you very much, all.
Thanks a lot, Professor.
Thank you, Professor. Bye.
Bye-bye, all.
Bye.